Alright, so let's just comment that we can use Stokes' theorem to go from the line integral of a vector field to the double integral over the surface of curl of f dot orientation vector n ds. And this is actually what we usually do. Okay. But of course we could go in reverse, right? Or in reverse, meaning that you could turn something that looks like that into something that looks like that. We won't try this today, but we will next time. So let's just go from this to that. Just to, it's the usual direction. Our last problem wasn't truly stated as an exercise. It was just verify the theorem. Now let's try a real exercise, the way that an exercise might be stated. Okay, so let f be the following vector field. F is equal to x squared minus y, comma 4z, comma x squared, and let's let capital S be the cone. Z is equal to root x squared plus y squared. For z less than or equal to 2, then let's use Stokes' theorem. Okay, probably a real problem doesn't actually state to use Stokes' theorem itself. We'll just use Stokes' theorem to find the line integral over the curve C of the vector field dot dr, where capital C, the curve, is the boundary of S, and this curve C is counterclockwise from above. So we could compute this line integral here directly, but instead we're going to use Stokes' theorem, meaning instead of doing this, we're going to set up this double integral over the surface instead. All right. So why don't we draw a picture first? X-axis, y-axis, z-axis. There's this cone here. Let's draw this thingy behind. There we go, just for a little perspective. 2 there. We've also got 2 here. Now S is parametrized by R of u comma v is equal to u cosine of v comma u sine of v comma u. At least this is an option, with the parameter domain capital D being 0 less than or equal to u less than or equal to 2 and 0 less than or equal to v less than or equal to 2 pi. For a normal vector, for the orientation of this surface, we'll work out that this should be r sub u let's actually correct this. This should be either a plus or a minus. We'll have to determine in a moment. But r sub u cross r sub v over the magnitude of r sub u cross r sub v. We'll work out, okay, plus or minus, and then this here is gonna, we'll save the details of the cross product and the partial derivatives, but negative u cosine of v, comma negative u sine of v, comma u over u root 2, and this will be either a plus or a minus. In the end, once we get that u root 2 in and we cancel the u's, we'll have here negative cosine of v over root 2, negative sine of v over root 2, comma 1 over root 2. Now, which sign do we take, plus or minus? Now, the thing is, we were told that we wanted the circle to be parametrized counterclockwise when viewed from above, meaning so if we stood up here and we looked down, this circle here, that would be capital C, and I traced over this in the direction we need to go. It's that way. That would mean that if we were to draw orientation that's going to be compatible, this cone, a point on the cone, we're not going to orient in the outward direction, okay? Because that would actually disagree. This blue circle here would actually disagree with the orientation shown in red. So what we need to do with a point, like let's say draw this, how do we do this? So like the point here needs to be oriented inward for compatibility. And that inward orientation means that this blue arrow is actually going to point slightly upward, which is why, because this right there, that k component is positive currently, we're going to need to take that plus sign here. So our orientation of the surface is with the plus sign. We'll have negative cosine of v over root 2, negative sine of v over root 2, comma positive 1 over root 2. Okay, so there's the orientation that we need. Let's go ahead and compute ds the way we normally would. For a surface given by parametrization, recall that ds is the magnitude of the cross product of partial derivatives. So r sub u, r sub v. We actually, and then dA. We actually already worked out this because it's in the denominator right here. So we get to recopy this u root 2. And then dA, let's just go with du dv to replace dA. Okay, so cool, we've got the ds part, we've got the n vector right here. We will also need the curl of f. Okay, so the curl of f. So we should take the vector field here that's given in the problem, and if we work out the curl of f, again, we'll skip that detail, we'll end up with the following vector field, negative 4, comma, negative 2x, comma 1. Let's go ahead and we're going to need to eventually write this in terms of u and v. So let's just replace the x that appears here with u cosine of v, and so we'll have here negative 4, comma, negative 2 u cosine of v, comma 1. All right, so then if we set up what Stoke's theorem here tells us to set up, so instead of computing the integral of the vector field directly, it's certainly an option. Instead of computing this directly, Stoke's theorem says we can do this instead. And so what we'll have here is going to be the integral sign, leave a little bit of space, integral sign, curl of f dotted with n. So if we take this vector field and dot it with this, so we'll have this times that, for example. So we'll end up with, let's see here, no, negative times negative, so positive. Okay, 4 cosine of v over root 2, and then, let's see, negative times negative, so that'll be positive as well, so plus 2 u cosine of v sine of v over root 2, and then finally 1 times 1 over root 2 as the last part of our dot product here, so plus 1 over root 2. And then we need to, so that let's see, we'll use a bit of color. So this takes care of that part. We now need ds right here, which we had computed right there. So right in this space, we need to write in a u root 2 du dv. Now, since we've set up a du dv integral and we have the parameter domain information up here, we're going to have the inner integral go from 0 to 2 and the outer integral, the v integral, go from 0 to 2 pi. So there we're set up. Let's just actually mention that this, if you go ahead and compute the integral, it's not that bad to do. I'd just say you got to distribute this, and the only, if at all anything, challenging integral to deal with is the cosine of v times sine of v. And really all you need to do in order to do that integral is use the fact that there's this trig identity that says sine of 2v is equal to 2 sine of v times cosine of v. So I would say give it a try, but in the interest of time we won't do this here. Now one last thing I'd like to mention, so we're done with that problem, is just to practice this orientation business, let's do this. If S is the portion of the cylinder x squared plus y squared equals 25. I know that just sounds like it should be a circle, but we're in three-dimensional space with z between 1 and 2 oriented outward. What is the boundary? Let's name the boundary C. So what is the boundary of S, but call it C, and what is its orientation? And its orientation. So we want a compatible orientation. Okay. So let's draw a picture. First off, that what we really have is, so let's see, x-axis, y-axis, z-axis, and so from z equals 1 to z equals 2, there's a circle here of radius 5, and let's just sort of looks like this. So there's the back side of that circle that's going to be hidden a bit, and then there's this, looks something like that. Okay, that's at least an attempt to draw this here. So if we orient this outward, meaning let's say like, this point, there's a vector that's pointing towards us. Here on the very edge of our view of this, there's a vector that would be pointing out this way. Imagine that thingy that we've seen, with the suction cup and so on. There should be an arrow for compatibility that should go counterclockwise should this thing be pointing at us. And so we should have orientation that looks like this, meaning actually this circle on the bottom should be oriented, based on like looking at that, should be oriented this way, whereas the circle that's on the top should be oriented that way. So what does C consist of? In here, so C is two circles, is really the union of two circles. And there's an upper circle, let's highlight that in blue, like here. And so there's an upper circle this way that's oriented like this. And then there's a lower circle. So if we use color to highlight that, that's this one down here, and then follows along the dotted line back here, and that circle is oriented this way. So you'll notice that the two circles are oriented in opposite directions from each other. If the lower circle here, viewed from above, is oriented counterclockwise, then the upper circle viewed from above is oriented clockwise.